All right, good afternoon, everyone. Let's get started. Before we talk about today's topic, there is one thing I would like to notice. The thing is, recitation time schedule has changed. It now starts from 9 p.m. and it ends at around 10 p.m. And another thing is we are providing the recording of recitation sessions as well. You first click the Colab of this recitation. And here you can check this recording button. And if you click this button, you are connected to the recitation video. All right. So you can check the recitation videos as well as the recitation Colab. All right. Okay, that was one quick notice. So are there any questions regarding course logistics or recitations? Cool, let's move on. Today we're going to talk about algorithm analysis. And these are what we're going to talk about today. First, I'm going to introduce what algorithm analysis is, and I'm going to give you a real world example. And then we're going to have a look at theoretical analysis, how we theoretically analyze algorithms. And I'm going to introduce the master theorem. And then I'm going to summarize this lecture. All right, first, introduction. What is an algorithm? An algorithm is, in general, a finite set of well-defined instructions that take some set of values as input and produces some set of values as output. And why do we do this? To solve a problem. So an algorithm is to solve a problem, and it receives a set of values as input and then produces some outputs. And in computer science, and what we are doing is computer science, right? A sequence of computational steps that transform the given input into the output for a given problem is what an algorithm is about, all right? So here, a well-defined instruction is here, computational steps, because we are dealing with computers. And why do we care about algorithms? Why do we study algorithms? Suppose that our computers are infinitely fast, and our computer can store infinitely many things, meaning that our computer has infinite memory spaces. Even in these cases, do we still need to study algorithms? The answer is yes. The reason is we would still like to demonstrate that our solution terminates. Even though our computers are infinitely fast, if it doesn't terminate, then our algorithm would not come up with the right solution. So we need to analyze our algorithm if it is going to terminate and produce the right, correct answers. And this is the second reason. We want to know that if our algorithm is going to produce the correct answer. So these are some reasons why we study algorithms. So basically, because our computers are not infinitely fast, so we want to find out some efficient algorithms, and that does not spend much memory spaces. So basically, we want to make efficient algorithms because our computers are not infinitely fast or have infinitely memory spaces. Now, of course, computers are not infinitely fast and do not have infinite memory spaces. And computing time is a bounded resource. So is space in memory. And we need to use these resources wisely or efficiently. That is the goal of studying algorithm analysis. And among several algorithms, we would like to choose the most efficient algorithm. Of course, we want to do this. And this process, choosing the most efficient algorithm, is called algorithm analysis. Basically, we are predicting the resources, space or time. So there are two types of complexities we are going to analyze. The first one is time complexity. And the second one is space complexity. However, among these two things, we basically or mostly concentrate on time complexity. So we focus on time complexity more than space complexity. Because in general, space might not be a big problem, but time becomes a big problem in most cases. So that is why we focus on time complexity rather than space complexity. All right, so that was the introduction. And from now on, I am going to give you a real world example. So here we're going to have a look at a problem. I'm going to describe this problem. What we are going to discuss is maximum contiguous subsequence subproblem. So what is this problem is about? First, we are given, so this is going to be our input, an array with integers. So we have n integers, array of n integers. And what we want to do is find, and this is going to be our output, find the maximum values of subsum. This is called subsequence sum over all possible choices of I and j. So this is summing some part of consecutive numbers. So k starts from I and ends at j. And we want to sum these numbers. So I'm going to give you one example. For example, if the input sequence is -2, 11, -4, 13, -5, 2, the answer is 20 because these three numbers in sequence produces the maximum subsequence sum. All right? So does everybody understand this problem formulation? If you can understand, please ask me your question. So this is our problem we're going to solve as an example. And we can come up with a naive solution. That is, you just naively check all possible choices of I and j. So we check all combinations of I and j and evaluate the subsequent sum. And among all those possible choices, we choose the maximum value. And how many subsequences do we need to check? How many subsequences are there? This is quite easy. The answer is we need to choose two numbers, I and j, between 1 and n. So that is this one, choosing two numbers, I and j. And this n corresponds to just single number. So if we say A1 is the maximum subsequence sum, that means I and j are both 1. So we are choosing just one number. So this corresponds to n combination 1. So if you sum these two numbers, it's going to be n squared over 2 plus n over 2. So this is all possible subsequences. All right. Now let's implement our naive solution together. So up to this point, are there any questions? All right, let's move on. So we are going to implement our naive solution. So let's say def max sum naive, and we are receiving an array. Let's call this array A simply. And we're going to define some variables to keep track of the maximum sum. And this is going to be our I, start and end. This is going to be our J. And what we are going to do is we're going to iterate through the length of A. So I becomes 1 and 0 through n minus 1, right? And we also need to iterate J. However, we are going to iterate J from I to the end of the sequence. So J is basically from I to the end of the sequence like this, all right? And what we are going to do is we're going to check the current subsum. So how can you evaluate the current subsum? We define another variable k, which changes from I to j plus 1. Then we're going to sum the subsequences to this sum variable. Okay. So if this sum is larger than max sum, we are going to assign sum to this max sum because this current sum is the maximum value of the subsequent sum, and start is going to be current I, and end is going to be current j. Okay. So we iterate I and j over all possible cases. And then for those all possible cases, we sum, evaluate. So this for loop is to evaluate the subsum for current I and j, right? And then we check or update our track. So we are keeping track of the maximum subsum and the start and end value, all right? And after we check all possible cases, we return the max sum and start value and the end value. So this is how we implement our naive solution, all right? Okay, let's get back to our slide. And let's analyze our naive solution. So what did he just do? To analyze our solution, what we are going to do is, rather than checking all possible operations, we'll only count the number of additions. So we are not going to care about like looping through A, I, and J. We do not care about these operations. We only count the number of additions because this operation takes the most of the time, and this assigning operations does not take much time. So this one is the major one. So we only take care about the addition, all right? So how many times do we add or call this expression that is expressed in this equation? We iterate I from 0 to n minus 1. And I told you that j here goes from I to n minus 1. So j here goes from I to n minus 1. And the number of addition here is j plus 1 minus I that is expressed here. So this is the number of additions in this algorithm, our function. All right? And how can you evaluate this? When we expand this one or put j, I here, then this value changes from 1 to n minus I. All right? And we know how to evaluate this expression, right? That is, we know 1, 2. If you want to sum from 1 to n, that is n times n plus 1 over 2, right? So we're just doing the same thing. N minus I plus 1 times n minus I over 2. And when we expand this one, here we are substituting n minus I as k. So n minus I becomes k. Then k changes from 1 to n, right? So we are substituting n minus I as k. And because I changes from 0 to n minus 1, if we put these two numbers here, then we know that k changes from n to 1. So we are just reversing the order of addition, and then we can say k changes from 1 to n, right? And when we expand this one is going to be k squared plus k. And we know that from high school mathematics that summing these k squared corresponds to this one, and k becomes this one, right? And because we have division by 2, that comes here, right? So when we expand this one once again, then it becomes n cubed plus 2n squared plus 4n over 6. So this is the number of additions that this function is conducting. All right, so this is how we analyze our algorithm. Any questions about analyzing this function in this way? So there was one question: what is the n in this equation? Here, n is the length of this array. So here, n is the length of the input array. Any other questions? All right, let's move on. And how can we improve our naive solution? Are there any suggestions? How can we improve our naive solution? This one is, of course, not the optimum one. Not optimal. Any suggestions to upgrade our algorithm? Okay, I'll give you 30 more seconds to think about how to improve our naive solution, and then we're going to discuss how we can approach this solution. All right, let's talk about how we can improve this algorithm together. The subsum from I to j, this one, can be obtained from the subsum from I to j minus 1 with only one addition. So what I mean by this is subsum from I to j can be regarded as subsum of I to j minus 1 plus aj. All right. So you can make this part more efficient. So this is our first PPP exercise. Try to implement the faster version. And before you start tackling this PPP exercise, please send me a PPP message. I'll give you one more minute. All right, let's implement this solution together. Thank you for sharing your answers. Here we're going to implement a faster version. And I'm going to define it as max sum faster. Even though you are not able to solve this problem, don't worry. I gave you like limited amount of time. So don't worry too much. So what we are going to do is optimize this part. All right. So how can you optimize this part? So rather than having another for loop, what we are going to do is just remove this part and move this sum here. And if you add the next sequence, then that is our current maximum subsum. All right. So we are going to just check if the current sum is maximum subsum. Here we need to change K to J. So that's all we need to do. So this one basically removes one for loop, and removing one for loop enhances the efficiency. All right. So this is our maximum subsum faster version. Any questions about this implementation? Okay, let's move on. Again, we're going to analyze this faster version. Here, we're going to count the number of additions once again. So what is the number of additions in this case? In this case, we're just looping through. This len A is what we call n, and this one is from I to n. So the number of additions here is simply n minus I, right? So that is what comes here. And we are iterating through I from 0 to n minus 1, because this value changes from I to n minus 1. So that is what comes here and here. All right. And when we expand this equation, that is going to be, we just put the value I here from 0 to n minus 1. Then this value becomes n minus 1 plus plus 1. And we know how to evaluate this value, right? This one is simply summing k from 1 to n. And that is n squared plus n over 2. And can you guys remember this number? This is what we just saw in the previous slide here. So we saw that this is the total number of subsequences we need to check, right? And our algorithm here, the faster version, does the addition, and this is exactly the number of possible subsequences, right? And this seems already quite good. We only look at each subsequence just single time. We do not look at each subsequence, all possible cases, more than once, right? And my question here is, can you do even better? And the answer is, amazingly, yes. We can use recursion to improve our solution. So how can you do that? This is another PPP exercise. Think about how we can categorize cases. So in the recursion class, we talked about what is recursion. Recursion is about breaking a big problem into smaller ones, right? So think about how we can categorize some cases and how we can call recursion function. All right, I'll give you like 1 minute. Please think about it. What are some cases? All right, let's think about how we can categorize and divide this problem into smaller problems. In fact, we can think of it as, let's say we have a sequence of numbers like this, and we divide this array into half. And we can divide this big problem into 3 cases. And the first case is the maximum subsum is in the left half, or the maximum subsum is in the right half. So that is the first and second cases. And the third case is the maximum subsum begins in the left half, so it starts from here, somewhere here, and ends in the right half, so here. So maximum subsum is located in this way. So these are 3 cases. And when we divide this big problem into small cases, there are 3 cases like this. And when you first see this approach, you might be wondering, this is quite simple. however, somewhat weird. However, you are going to see this approach, this kind of approach, more than several times towards the end of this course, okay? So you need to become familiar with this kind of approach. And now let's implement this recursive version together. So we implemented a naive solution and we improved it by optimizing this for loop. And what we are going to do now is implementing using recursion. All right. So here I'm going to define this function as def max sum recursive. And our function needs to receive different parameters than this one. Because we want to use recursion, we need to define or design our function in a somewhat different way. So here we are going to receive our input array as well. However, what we are going to do is receive also a left index and the right index. So we only care about the numbers between left index and the right index. So when we do this, when we actually want to use this function, what we are going to do is max sum recursive driver. And this function only accepts the input array. And what we are going to do is, if the length is larger than 0, then we are going to call max sum recursive a0 len a minus 1. So in the first case, we are checking all the numbers from the start to the end. However, this function cares only about the numbers between the left index and the right index given. All right. If the length of this array is, if this array does not contain any element, then we just need to return 0. All right. So this is how we are going to use this function. And let's implement this one. So what is the base case? The base case is when the left index equals to the right index. So this is our base case. So in our base case, we need to check another thing. If this number is larger than 0, then we're going to return this number. However, if this number is negative, then we are going to return 0 because we are not going to add this negative number. All right, so that is our base case. So here we're going to divide our problem into smaller ones. So this is our body. And I told you that there are 3 cases. That the first case is the maximum subsum is on the left part, and the second case is the maximum subsum is on the right part. So we're going to implement those cases first. And to do that, we first need to define or find the standard index. The standard index is simply sum left and right indices and divide it by 2. And the maximum subsum on the left part is just by calling this function on the left part. So we are going to pass the same a, and we are going to check the left half. So this is going to be our first case. So this is our first case. And what was our second case? The maximum subsum is on the right side, right? then we're going to call center plus 1 to right. So this is our second case. Okay, so implementing the first and second cases are quite easy. We just call our recursive function in this way. And from now on, we're going to implement our third case. And to implement our third case, we need to define some variables to keep track of the maximum subsum. We're going to define some numbers like this: max border sum left, max border sum right, and these two numbers are initiated as 0, and left border sum, right border sum. And what we are going to do is we're going to iterate I So what we are going to do is, let's say, this kind of array. And this 6 or 5 is going to be our center. And what we are going to do is move to the left one by one. So we start from center and move towards the left boundary. In the first case, the boundary is 0 anyway. And so the idea is we start from the center and move towards the left part one by one and check if this sum becomes larger and larger. All right, so that's what this is doing. So we start from center and goes towards left part by decrementing I minus 1. And our left border sum is just adding the number at that position. All right. And if this left border sum is larger than the maximum border sum left, then we are going to update this maximum border sum left with the current left border sum. All right. And what we are going to do next is do the same thing on the right half side. So in this case, we change our I from center plus 1 to right plus 1. So we start from center and move to the right side one by one. And we are basically doing the same thing. Right border sum plus AI. And if right border sum is larger than max border sum right that we're keeping track of, then we are updating this number with the current right border sum like this. Okay, so this is our third case. So the third case is going to be max border sum right plus max border sum left. So this is our third case. And what we are going to return is maximum of among these three numbers. So max sum left and max sum right and max sum center. So among these three numbers, we're going to return the maximum one. All right, so this is the recursive implementation of subsum, finding the maximum subsum. All right, so are there any questions about this implementation? All right, and let's compare these three solutions. So this is some test code that is going to compare the subsum. So algorithm 1 takes 36 microseconds, and algorithm 2 takes 60 microseconds when n is 10. And our recursive version takes longer time when n is 10. However, when n becomes 100, the third solution, our recursive version, becomes faster. I told you about this, right? Because recursion entails function call. Sometimes it becomes slower when n is small. However, when n becomes 1000, then the naive solution becomes very, very slow. However, the second one, our faster version, is much faster than the first one. And our recursive version is even faster than the faster version. All right. So this demonstrates that efficient algorithms are very important. We can use our resources very efficiently. All right. So let's analyze our recursive version together. How are we going to analyze our recursive function? The key insight here is that it takes n over 2 plus n over 2, which is n additions, to compute the third case. Let's see what this means. So here we're starting from the center and moves toward left part with one step. And we start from center, move towards right with step size of 1. So these two for loop in total takes only n additions. Can everybody understand this part? And to compute these two cases, we are dividing our sequence into half, the left half and right half. All right. So if we say the total number of computations required for this algorithm or this function, let's say that is Tn. And if n is 1, then it takes only 0 computation because we just return that number. Otherwise, we are going to divide our sequence into left half or right half and call our maximum subsum recursive function here and here. So that corresponds to these parts. So this one is first and second cases, and this one corresponds to the third case. All right. And how are we going to solve this recursive equation? So this is basically this one. To solve this recurrence equation, it takes some discrete mathematics. Let's just claim that when we input 2 to the power of k, then it becomes k times 2 to the power of k. And we are going to prove that this one holds for every possible input. So let's do that. Can you prove this recurrence equation becomes this one using mathematical induction? Think about it on your own. I'll give you 2 minutes. And Seungjae asked this question. When we were talking about recursive implementation, I implemented two functions. The first one was, so I'll explain this part. The first one was our recursive version. However, this one receives left index and right index. So we cannot just pass our input array into this function. So we just need to make another function to deal with the first case, or just receive the input array, because the users do not know how to use this function. Okay, so when you think about other functions, they just receive the input array. However, this one looks different. Okay, so for users, we are going to just accept the input array, and we are going to pass the first elements index and the last elements index. Then this function takes care about the elements between these two numbers. So for the first case, we need to take care about all the numbers inside this array. So that's why we are passing 0 and len a minus 1. Does this answer your question, Seungjae? All right. Try to prove this by mathematical induction. I'll give you one more minute. All right, let's prove this recurrence equation together. The base case is when k equals 0, if we're just putting k equals 0 here and here, then that is t1, which is 0. Because we claim that stated that when n equals 1, then the output is 0. All right. So for the base case, this claim is true. And we are going to think about the inductive step. If k is larger than 0, we assume that t to the power of k minus 1 equals this one. So we're just assuming that when k n is k minus 1, this one holds. Then t to the power of k, you are going to use this part. It's going to be 2 to the power of k minus 1 times 2, plus here we are substituting n as 2 to the power of k. So we are putting 2 to the power of k here. And we know that this one is k minus 1 times 2 to the power of k minus 1. So we are putting this value here. And here we have 2. And by combining these 2 to the power of k minus 1 and 2, it's going to be k times 2 to the power of k. So we just proved that using mathematical induction, that t 2 to the power of k becomes k times 2 to the power of k. And we are just returning back to n because 2 to the power of k is n. K becomes log n, right? And we are putting this value here, then Tn, because n times log n. And this one is smaller than n squared, right? So that is why recursive implementation is faster than the faster version. All right. So any questions about this proof? All right, thank you for your feedback. As we saw in our experiment, when n becomes larger and larger, the speed gap becomes larger as well. And so this one was naive solution. This one was faster version. This one was recursive version. And for n equals 10 to the power of 6, the naive solution requires 3 times 10 to the power of 17 computations, while the faster version requires 5 times 10 to the power of 11. Whereas the recursive solution takes 2 to the power of 10, 2 times 10 to the power of 7. For 1 gigahertz processor, this means it could perform 10 to the power of 9 additions per second. So when n becomes 10 to the power of 6, the naive solution requires 3 times 10 to the power of 8 seconds. This one is same as 10 years. And the fast solution requires 5 times 10 to the power of 2 seconds, which is same as 8 minutes. And the recursive solution takes only 20 milliseconds using the same 1 gigahertz processor. So this one demonstrates that efficient algorithms really saves the computation. All right. So now you might all of you might understood the importance of efficient algorithms. However, I told you that when n was small, recursive solution was slower than a faster version. I told you that recursion entails function calls, and function calls sometimes requires more overhead. And you better weigh between the overhead and performance gain. So when n is small, you might use the faster version. And when n becomes larger, then you might turn to recursive solution. And my last question is, our recursive solution was quite amazing. However, the fact is, we can do even better than our recursive solution. And you can think about how we can improve our recursive version. And this might be one of our homework problems. And another takeaway from our class is when you see these implementations, the faster version is shorter than the recursive solution. The recursive solution is quite longer than this faster version. So shorter implementation or constant implementation don't necessarily mean that they are more efficient. Okay, so even though your code or your implementation can be longer, but it could be more efficient. Okay, and from now on, we're going to talk about theoretical analysis. Counting the number of primitive operations that an algorithm executes in the worst case on an input of size n is what we are going to do. Since all primitive operations take constant time on modern computers, so we are just count the number of primitive operations like addition, subtraction, or multiplication, division, like this. If the fastest primitive operation takes time A and the slowest time B, and the algorithm of interest uses P and primitive operations, then the total number of operation is bounded by B times Pn and A times Pn. So our computation is bounded by these two numbers. And examples of primitive operations are assigning a value to a variable or calling a method, arithmetic operations, adding two numbers, or indexing into an array, or following a reference, returning from a method, these kind of things. We are actually more interested in the growth rate of the running time rather than the exact number of additions or exact number of primitive operations. The growth rate indicates how fast the running time increases when the size of input increases. So why is this important? Because the growth rate determines the scaling behavior, as we saw in the previous example. So when n was small, the three solutions came up with a solution with a similar amount of time. So when n is small, you don't need to care about whether it is efficient or not. However, when n becomes larger and larger, the time gap become larger as well. So the time complexity, let's say the time complexity is n or n squared n cubed 2 to the power of n. Problem size after speed up becomes 10 times like this. And there is one big, so we are going to here introduce some notations to describe the complexity growth rate of our algorithms. The first one is big O notation. So big O notation represents the growth rate of an algorithm, and the goal is to specify the bounding from above. So let's have a look at this graph. So let's say this fx, this function, is bounded by 2 times gx. So this one is smaller than 2 times gx all the times. Then we could say when x is here, this one is x-axis, this one is y-axis. When x is larger than 1, then this function is always smaller than 2 times gx. Then we say f is in G's bounded above family, or f is inside big O of gx. Even though fx is larger than gx, but smaller than 2 times gx, we don't care. If we can multiply some constant, and this gx could be larger than this fx when x is larger than 1, then we just say fx is inside g's bounded above family. So more precisely, we say that fx is inside the big O family of gx if there is a real number c larger than 0 and an integer n0 that is larger than 1, such that fn is always smaller than c times gn for n larger than n0. So if, let's say, this value is like 3, even in this case, or 3 or 2, even in this case, we say that f is inside the big O family of gx. All right? And there is another notation that is called big omega notation. This is similar to big O notation. We're going to specify the bounding from below. So we're going to focus on the lower bound. Here, f prime x, this f prime x is larger than 0.5 times gx, as long as x is larger than 1. Then we say f prime x is in g's bounded below family, even though f prime x is smaller than gx everywhere. All right? So more precisely, if we can find the real constant number c larger than 0 and an integer n0, such that fn is always larger than c times gn when n is larger than n0, then we say f is inside the big omega of g. Okay, you just need to find g and n0, c and n0. And as you saw these two examples, then you could say that, oh, the same g can be a big family of so you can think about this case. So the same g can be a big O of f as well as the big omega of f. This is possible, okay? So you just need to be able to find this constant c and this n0 integer. And the last notation we're going to think about is big theta notation. In the two previous slides, we not only have f was a family of big OG, and f prime x was family of omega g, but also this one happened. This is what I told you in the previous slide. In this case, we say that fx is the family of big theta of g. So if g is big omega of f as well as big omega of g, then we say f is in the family of big theta of g. Okay? So if we say f is in the family of big theta of g, that means g can be the family of big O and the family of big omega for f. So this is our notation. And we represent the complexity with the simplest form. So let's say the time complexity of this one, we do not care about these small numbers and even the constant. As you saw in the previous slides, for the definitions of big omega, big O, big theta notations, we don't need to care about these constants. We only care about this number. So the simplest term becomes big O n squared. And in this case, we remove the smaller time complexity terms and the constant, and we just say time complexity of this algorithm is big O n cubed. In this case, we do not care about these numbers, and the time complexity becomes big O of log n. In this case, we will remove this part and remove this part. So when we basically analyze some algorithms, we usually use the big O notation. So that is the best basic case. The reason is, let's say when n becomes these values, and these are some time complexities. As you can see here, when n becomes very large, like this, when you compare 2 to the power of n and 2 to n's cube, you don't have to care about this number because the dimension is different, very, very different. Even though you multiply like 1,000 or 10,000, any numbers, it is much, much larger than n cube. So we do not care about n cube when there is 2 to the power of n. And when you look at these two terms, n log n becomes meaningless compared to n squared when n is large, like this. So we do not care about this term, but only this term, okay? So this is why I only care about the biggest terms and remove the smaller terms. And this is going to be, I guess, the last PPP exercise of today. Sort the functions in the increasing order of big O complexity. Think about it for like 2 minutes. All right, thank you for sharing your answers. The answer is F3 is the largest, F4 is the second, F2 is the third, and F1 is the least big O complexity, right? All right, we are going to talk about from this slide next time. Let's call it a day. Thank you for your participation.